October 23, 1944. Leyte Gulf, Philippines. First Lieutenant Robert Wade settled into the cockpit of his F4U Corsair aboard USS Essex, running through pre-flight checks as dawn broke over the Philippine Sea. The aircraft carried 6 Browning A&M-2 machine guns, 3 mounted in each wing, each weapon loaded with 400 rounds of 50 caliber ammunition, fed through disintegrating link belts that would prove revolutionary in ways Wade could not yet fully comprehend. Through the salt-streaked windscreen, Wade watched deck crews scramble across the carrier's flight deck, preparing the morning's first strike against Japanese positions defending Leyte. The mission briefing had been straightforward: provide air cover for Navy bombers attacking Japanese shipping in Ormoc Bay, engage any intercepting fighters, and suppress anti-aircraft positions along the coast. Standard escort work that every Corsair pilot had flown dozens of times. What made this morning different was what Wade and his squadron mates had discovered during their previous missions. Their guns simply did not jam. The Browning machine guns mounted in Corsair wings fired continuously through engagements that would have left earlier aircraft helpless with jammed weapons. Pilots were returning from combat having expended all 2,400 rounds without a single stoppage, achieving sustained firepower that Japanese pilots had never encountered and could not match. The technical innovation that enabled this capability seemed almost mundane in its simplicity. Metal links that separated from the ammunition belt as each round was fired, falling away rather than being pulled back through the gun mechanism. This disintegrating link system, perfected by American ordnance engineers during the late 1930s, had transformed the Browning from an excellent weapon into the most reliable aircraft machine gun of World War II. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Browning A&M-2 machine gun represented the aircraft variant of John Browning's M2 heavy machine gun, a weapon design that had entered service with the United States Army in 1933. The aviation version incorporated modifications for installation in fighter aircraft. Reduced weight through aluminum components rather than steel, pneumatic charging mechanisms that allowed pilots to cock the weapons from the cockpit, and most critically, feed systems designed to handle the sustained fire rates that aerial combat demanded. Each gun weighed 61 pounds and measured approximately 65 inches in length. The barrel alone stretched 36 inches, containing rifling that spun 50 caliber projectiles at 2,700 feet per second as they left the muzzle. The ammunition itself was formidable. Each 50 caliber round measured over 5 inches in total length, with a projectile diameter of 0.5 inches, weighing between 600 and 700 grains depending on projectile type. The cartridge contained enough propellant to generate chamber pressures exceeding 50,000 pounds per square inch, driving the projectile to velocities that could penetrate armor plate at ranges exceeding 1,000 yards. When 6 of these weapons fired simultaneously, as they did in the Corsair, they delivered a combined rate of fire approaching 4,800 rounds per minute, creating a cone of destruction that could soar through enemy aircraft structures or shred ground targets in seconds. The challenge had always been feeding ammunition into these weapons reliably under combat conditions. Early aircraft machine guns used fabric belts that held cartridges in pockets sewn into canvas material. These fabric belts worked adequately at slower fire rates and in temperate conditions, but they absorbed moisture that caused swelling. They stretched under tension, and they deteriorated rapidly when exposed to salt spray, tropical humidity, or temperature extremes. Fabric belts also had to be pulled completely through the gun mechanism and ejected after firing, requiring space for both the incoming ammunition belt and the outgoing empty belt, complicating installation in aircraft wings where volume was precious. Metal link belts represented a significant improvement over fabric. Individual metal links held cartridges securely while remaining flexible enough to feed smoothly through gun mechanisms. These links were far more durable than fabric, unaffected by moisture or temperature, and they could be loaded and unloaded repeatedly without degradation. However, early metal link designs shared one critical limitation with fabric belts. They had to be pulled completely through the gun and ejected after firing. This requirement meant that gun installations needed ejection chutes for spent links, adding weight and complexity to aircraft installations. More problematically, the spent links themselves could cause malfunctions if they did not eject cleanly or if they tangled during ejection. The disintegrating link system solved these problems through elegant simplicity. Each link consisted of stamped metal formed into a shape that held a single cartridge while connecting to adjacent links through small tabs that interlocked under tension. As the gun's feed mechanism pulled a cartridge forward to chamber it, the link holding that cartridge separated from the belt and fell away, typically through an ejection port in the bottom of the gun or simply dropping out of the wing after the cartridge was extracted. The remaining belt stayed intact, continuing to feed subsequent rounds without interruption. This meant the gun only had to handle incoming live ammunition, not outgoing empty links, simplifying the feed mechanism and eliminating an entire category of potential malfunctions. American ordnance engineers at Springfield Armory had developed the disintegrating link system during the 1930s, specifically to address reliability problems observed during testing of aircraft machine guns. The engineers recognized that aircraft installations created unique challenges compared to ground-mounted weapons. Guns in aircraft wings operated while subject to violent maneuvering forces, temperature extremes from ground level to high altitude, and exposure to moisture and contaminants. They had to function reliably whether the aircraft was in level flight, a vertical climb, an inverted dive, or a 9G turn. Any feed system that depended on gravity or required precise alignment would inevitably fail under combat conditions. The disintegrating link design proved remarkably tolerant of these harsh conditions. The links themselves were stamped from spring steel in a process that required minimal machining, making them inexpensive to manufacture in enormous quantities. Each link weighed less than 1 ounce, and the steel composition provided enough flexibility to absorb shock without breaking, while maintaining enough rigidity to feed reliably. The cartridge sat in a groove, formed by the link's shape, held securely by friction and the pressure from adjacent links. This simple mechanical arrangement worked reliably regardless of aircraft attitude, G-forces, or environmental conditions. Production of disintegrating link ammunition began at Lake City Army Ammunition Plant in Missouri during 1941 as the United States prepared for war. Lake City, operated by Remington Arms under contract to the War Department, had been constructed specifically to manufacture small arms ammunition at unprecedented scales. The facility covered nearly 4,000 acres and employed over 20,000 workers at peak production, operating 24 hours per day through multiple shifts. Assembly lines stamped out disintegrating links by the millions, loaded them with .50 caliber cartridges, and packaged them in metal containers designed to protect the ammunition during shipment across thousands of miles of ocean to forward bases throughout the Pacific. The manufacturing process reflected American industrial efficiency applied to ordnance production. Raw brass arrived by rail car was formed into cartridge cases through progressive stamping operations, then filled with propellant, fitted with primers, and topped with projectiles in continuous assembly line operations that minimized handling and maximized throughput. Simultaneously, steel coil stock was fed into stamping presses that produced disintegrating links at rates exceeding 10,000 per hour per press. Quality control inspectors sampled production continuously, testing links for proper dimensions, spring tension, and feed reliability using specially designed test fixtures that simulated gun feed mechanisms. Each completed belt contained cartridges linked together in precise spacing that matched the feed mechanism geometry of the Browning ANM-2. The standard loading configuration for Corsair installation consisted of 400 rounds per gun, arranged in a continuous belt that weighed approximately 130 pounds fully loaded. These belts were coiled into cylindrical ammunition boxes that fit into the wing structure adjacent to each gun, positioned so that the belt could feed smoothly into the weapon without sharp bends that might cause feed problems. The ammunition boxes themselves were engineering marvels of compact design, incorporating feed chutes that guided the belt into the gun while providing protection from combat damage. Armament crews loading Corsairs aboard carriers became intimately familiar with these ammunition systems through countless loading operations. The standard procedure required 2 men working together to install each ammunition box, carefully routing the belt through the wing structure to connect with the gun's feed mechanism, then verifying that the belt moved freely without binding or misalignment. Once installed, the system required minimal maintenance beyond keeping the guns clean and properly lubricated. The disintegrating links themselves needed no attention. They simply worked, feeding round after round without the adjustments and troubleshooting that earlier belt systems had demanded. Japanese aircraft machine gun technology had developed along a different path, one that would prove significantly less reliable under sustained combat conditions. The Imperial Japanese Navy's standard fighter armament consisted of 2 7.7mm Type 97 machine guns and 2 20mm Type 99 cannon. The machine guns used fabric belts that had to be pulled through the weapon and ejected, while the cannon employed belt feeds with metal links that similarly had to transit the entire weapon before being discarded. Both systems worked adequately under ideal conditions, but proved vulnerable to malfunctions when stressed by violent maneuvering, environmental extremes, or sustained firing. The Type 97 machine gun, derived from the British Vickers design, fired rifle-caliber ammunition that lacked the destructive power of American .50 caliber rounds. 200 rounds of 7.7mm ammunition carried less projectile mass than 100 rounds of .50 caliber, and the lighter bullets lost velocity and energy more rapidly with distance. Japanese pilots compensated by mounting cannon that fired explosive shells with devastating effect when they hit, but the 20mm Type 99 cannon carried only 60 rounds per gun and suffered from relatively slow rates of fire compared to machine guns. More critically, the cannon's belt feed mechanism proved prone to jamming, particularly during negative G maneuvers, or when the aircraft pulled high G turns that subjected the ammunition belt to forces it was not designed to withstand. Japanese maintenance procedures reflected the reality that their aircraft weapons required constant attention. Ground crews spent significant time adjusting belt tension, cleaning feed mechanisms, and troubleshooting stoppages that occurred during test firing. Japanese pilot training emphasized ammunition conservation precisely because pilots could not rely on their weapons to function continuously through extended engagements. Doctrine called for short, accurate bursts rather than sustained fire, partly because sustained fire increased the probability of jamming, and partly because limited ammunition capacity made conservation essential. American pilots, by contrast, received training that emphasized different principles entirely. Gunnery instructors at advanced training bases taught pilots to fire in bursts lasting 2 to 3 seconds, long enough to walk tracers onto target and achieve hits, but not so long as to waste ammunition. However, the reliable feeding of the AN-M2 meant that pilots could and did fire longer bursts when situations demanded, knowing that their weapons would continue functioning. Combat reports from Corsair squadrons throughout 1944 and 1945 document numerous instances where pilots fired sustained bursts, lasting 5 seconds or longer without experiencing stoppages, expending hundreds of rounds in single attacks. The psychological impact of this reliability cannot be overstated. A pilot who knows his weapons will fire when he presses the trigger can focus entirely on tactics, positioning, and achieving firing solutions. A pilot who worries that his weapons might jam at critical moments must constantly manage that uncertainty, holding fire until optimal conditions exist, limiting burst length to reduce jamming probability, and accepting that mechanical failure might prevent him from defending himself or completing his attack. This psychological burden, invisible in technical specifications but profound in combat effectiveness, represented a significant Japanese disadvantage that worsened as the war progressed, and Japanese maintenance quality deteriorated. The Corsairs' installation of 6 Browning AN-M2 machine guns created a weapons system that delivered unmatched reliability combined with overwhelming firepower. The 3 guns in each wing were staggered to fit within the wing's internal structure, with feed mechanisms positioned to draw ammunition from boxes mounted inboard of the guns. When all 6 weapons fired simultaneously, they produced a sound described by pilots as a deep, resonating roar that could be felt through the aircraft's structure. The recoil from 6 guns firing together created noticeable deceleration, momentarily slowing the aircraft by several miles per hour, but Corsair pilots learned to anticipate this and incorporated it into their gunnery technique. The ballistic performance of 6 50 caliber machine guns firing armor-piercing incendiary ammunition created destruction far exceeding what lighter caliber weapons could achieve. Each projectile carried enough kinetic energy to penetrate aluminum aircraft structures, sever control cables, puncture fuel tanks, and damage engines. The incendiary compound within armor-piercing incendiary rounds ignited upon impact, starting fires that could rapidly consume fabric-covered control surfaces or detonate fuel vapor in partially empty tanks. When multiple rounds from 6 guns converged on a target simultaneously, the cumulative effect often resulted in catastrophic structural failure or immediate fires that destroyed the target within seconds. Combat action reports from October and November 1944, as Marine and Navy Corsair squadrons supported the Philippines campaign, documented the devastating effectiveness of this weapons system. Pilots consistently reported that Japanese aircraft disintegrated or caught fire after brief engagements, often requiring only a single burst to achieve kills. The reliability of the disintegrating link feed system meant that pilots could engage multiple targets during single missions, firing at the first target until it was destroyed, then immediately engaging subsequent targets without worrying whether their guns would function. This sustained combat capability multiplied the effectiveness of each Corsair, allowing individual pilots to achieve multiple kills during missions where earlier fighters might have been forced to disengage after engaging a single target. Lieutenant Robert Wade's mission on October 24th proceeded according to plan through the early morning transit to Leyte. The strike group consisted of 12 Corsairs providing escort for 18 SB-2C Helldiver dive bombers tasked with attacking Japanese transports in Ormoc Bay. Japanese fighters intercepted the formation as it approached the target area, with approximately 20 Mitsubishi A6M0 fighters diving from altitude to engage the American aircraft. Wade's division broke left to intercept the lead Japanese elements, maneuvering to achieve firing positions, while the bombers continued toward their targets under protection from the remaining Corsair divisions. Wade achieved his first firing opportunity as a Zero pilot attempted a head-on pass against the bomber formation. The geometry provided only a brief window, perhaps 2 seconds, when the Zero would be within effective range before passing through the formation. Wade pressed the trigger, feeling the characteristic deceleration as all 6 guns began firing, watching his tracers arc toward the rapidly closing target. The Zero's canopy shattered, the fuselage disintegrated midsection, and the aircraft tumbled past trailing flames and debris. Wade had fired approximately 300 rounds in that single burst, and when he released the trigger, all 6 guns were still functioning perfectly. The engagement continued for another 8 minutes as Corsairs and Zeros maneuvered through the airspace above Ormoc Bay. Wade achieved firing solutions on 2 additional targets, destroying both with bursts that consumed another 400 rounds. Other Corsair pilots reported similar results, with the squadron collectively claiming 11 Japanese aircraft destroyed during the engagement. When Wade landed back aboard Essex, his aircraft's ammunition boxes were empty, all 2,400 rounds expended without a single malfunction. The armament crew that reloaded his guns noted this in their maintenance logs, recording that all 6 weapons had functioned flawlessly through the entire sortie. This pattern repeated across Corsair squadrons throughout the Philippines campaign. Pilots consistently reported that their weapons worked exactly as designed, firing continuously until ammunition was exhausted. The disintegrating link feed system had proven itself under the most demanding conditions imaginable. Violent combat maneuvering, sustained high G loads, temperature variations from sea level to 20,000 feet, and exposure to salt spray and tropical humidity, where Japanese weapons jammed frequently enough that pilots planned tactics around anticipated stoppages, American weapons simply worked, providing the reliable firepower that allowed Corsair pilots to dominate aerial engagements. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese naval aviation intelligence began documenting American aircraft weapons reliability during late 1944 through analysis of combat reports and interrogation of pilots who had survived engagements with Corsairs. The pattern emerged clearly from accumulated evidence. American fighters maintained sustained fire through entire engagements without apparent weapon malfunctions, while Japanese aircraft experienced frequent stoppages that left pilots defenseless at critical moments. Technical officers examining damaged American aircraft recovered from crash sites noted the disintegrating link ammunition systems and immediately recognized their significance. The Japanese had developed their own aircraft machine gun and cannon designs based primarily on licensed European technology acquired during the 1920s and 1930s. The Type 97 machine gun derived from the British Vickers design, while the Type 99 cannon represented Japanese development of the Swiss Oerlikon 20mm weapon. Both designs worked adequately when manufactured to proper specifications and maintained by skilled armourers, but Japanese industrial capacity had never matched American production quality, and by 1944, manufacturing standards had deteriorated significantly as raw material shortages and strategic bombing degraded industrial capability. Japanese ammunition production faced constraints that American industry never encountered. Copper for cartridge cases became increasingly scarce as the war progressed, forcing Japanese manufacturers to use steel cases that were more prone to extraction failures and feed problems. Quality control suffered as experienced workers were conscripted for military service and replaced with minimally trained personnel who lacked the skills to maintain manufacturing precision. The fabric belts used for machine gun ammunition deteriorated in tropical storage conditions, absorbing moisture that caused dimensional changes and feed reliability problems. Japanese maintenance personnel in forward areas struggled with inadequate supplies of spare parts, replacement barrels, and cleaning materials necessary to keep weapons functioning. The cumulative effect of these industrial and logistical problems meant that Japanese aircraft weapons became progressively less reliable as the war continued. Pilots who had trained on weapons that functioned adequately during 1942 and early 1943 found themselves flying aircraft in 1944 and 1945, where weapon malfunctions had become routine occurrences expected during every mission. Japanese tactical doctrine evolved to accommodate this reality, emphasizing hit-and-run attacks that minimized the time spent in combat and the number of firing passes attempted. Pilots learned to make every shot count because they could not rely on being able to fire continuously if their initial attack failed to destroy the target. American pilots faced no such constraints. The industrial capacity that produced disintegrating link ammunition by the hundreds of millions of rounds ensured that every aircraft launching from carriers or island bases carried fresh, properly manufactured ammunition that would feed reliably, regardless of environmental conditions or combat stress. The Browning AN-M2 mechanism itself, manufactured to specifications that maintained tight tolerances through rigorous quality control, rarely experienced parts failures even after firing thousands of rounds. When malfunctions did occur, they typically involved obvious problems like damaged ammunition or improperly installed feed mechanisms, issues that could be identified and corrected through standard maintenance procedures. The reliability advantage compounded over time as American logistics ensured continuous supplies of replacement barrels, spare parts, and fresh ammunition reached forward units without interruption. Corsair squadrons operating from carriers received complete ammunition reloads after every mission, with armament crews replacing any gun that showed signs of excessive wear or malfunction. Japanese squadrons operating from increasingly isolated island bases struggled with deteriorating weapons that could not be properly maintained due to lack of spare parts, cleaning materials, and qualified armourers. By early 1945, some Japanese fighter units reported weapon malfunction rates exceeding 50%, with more than half their aircraft experiencing stoppages during combat missions. The contrast in pilot confidence reflected these technical realities. American pilots trusted their weapons absolutely, knowing from experience and training that the Browning machine guns would fire when needed. This confidence enabled aggressive tactics that capitalized on the Corsair's speed and firepower advantages, allowing pilots to press attacks knowing they could deliver sustained fire that would destroy targets. Japanese pilots operated with the constant awareness that their weapons might fail at any moment, forcing them to be more cautious in their attacks and more conservative in their ammunition expenditure. This psychological disadvantage, subtle but pervasive, affected every tactical decision and every combat engagement. December 1944 brought intensified operations as American forces prepared for the invasion of Luzon, the main Philippine island. Corsair squadrons flew continuous combat air patrols over the invasion fleet, intercepted Japanese air attacks, attempting to strike American ships, and provided close air support for ground forces fighting their way across the islands. The sustained tempo of operations stressed every aspect of aircraft and weapons systems, revealing which designs could maintain performance under continuous use and which would fail when most needed. The Browning AN-M2 excelled under these demanding conditions. Armament crews aboard carriers developed efficient procedures for rapid turnaround, reloading all 6 guns on a Corsair in under 20 minutes when working without interruption. The disintegrating link ammunition system simplified this process significantly compared to earlier belt systems that required careful threading through complex feed mechanisms. Armament crews simply opened the ammunition box access panels, lifted out the empty boxes, installed fresh boxes loaded with new ammunition belts, connected the belt to the gun's feed mechanism, and verified proper alignment. The entire operation required no adjustments, no special tools, and minimal training beyond basic procedures that any competent mechanic could master quickly. Japanese maintenance procedures, by contrast, required significantly more time and skill to reload weapons and clear malfunctions. The fabric belts used in machine guns had to be carefully inspected for damage before loading, as any tears or worn areas would likely cause feed failures. The cannon belt feeds required precise adjustment of tension and alignment to function reliably, adjustments that were difficult to maintain as components wore through use. Japanese armament crews spent substantial time troubleshooting and repairing weapons between missions, time that reduced aircraft availability and limited the sortie rates Japanese units could sustain. Combat effectiveness metrics from the Philippines campaign demonstrated the cumulative impact of American weapons' reliability advantages. Corsair squadrons consistently maintained higher sortie rates than Japanese units of equivalent size, launching more missions per day because their aircraft spent less time undergoing weapons maintenance. When Corsairs did engage Japanese aircraft, they achieved kills more rapidly, typically destroying targets within seconds of achieving firing solutions rather than requiring multiple attack passes. The sustained firepower made possible by reliable disintegrating link feed systems allowed individual Corsair pilots to engage multiple targets during single missions, multiplying their effective combat power. Statistical analysis of air combat during the Philippines campaign shows that Corsair units achieved kill ratios approaching 12-1 against Japanese fighters, with individual squadrons reporting even more favorable ratios during specific operations. While multiple factors contributed to this superiority, including the Corsair's speed advantage, pilot training quality, and tactical doctrine, weapons reliability formed an essential foundation that enabled other advantages to be fully exploited. A faster aircraft with better trained pilots achieves nothing if its weapons jam when firing solutions are achieved. The Browning AN-M2 with disintegrating link feeds ensured that Corsair advantages translated directly into combat success. January 1945 brought the invasion of Luzon and the beginning of the final campaign to recapture the Philippines. Marine Corsair squadrons operating from escort carriers provided continuous close air support for ground forces, flying dozens of sorties daily against Japanese positions, defending Manila and surrounding areas. These ground attack missions stressed aircraft weapons differently than air-to-air combat, requiring sustained fire against hardened targets like bunkers, pillboxes, and fortified positions. The Browning machine guns proved equally effective in this role, their .50 caliber projectiles penetrating typical field fortifications and suppressing Japanese defensive fire. Ground attack missions typically involved multiple strafing runs against assigned targets, with pilots making successive passes to saturate target areas with machine gun fire. During these attacks, Pilots often fired continuous bursts lasting 3 to 5 seconds, walking their fire across target areas to ensure coverage. The disintegrating link feed system handled these sustained firing sequences without difficulty, maintaining consistent feed rates, regardless of aircraft attitude or maneuvering loads. Pilots reported that they could roll inverted, dive vertically, or pull high G turns while firing without experiencing feed problems, a level of reliability that earlier belt systems could not match. Japanese forces defending Luzon experienced the full weight of American firepower superiority, as Corsairs and other American aircraft flew thousands of sorties supporting the ground offensive. Japanese troops in defensive positions reported that American strafing attacks delivered sustained fire that did not pause or slacken, indicating either that American weapons did not jam or that they were quickly cleared and resumed firing. The reality was that American weapons rarely jammed in the first place, a reliability advantage that Japanese forces could observe, but not counter with their available weapons and industrial capacity. February 1945 saw American forces preparing for the invasion of Iwo Jima, a heavily fortified island that Japanese commanders had turned into the most formidable defensive position in the Pacific. Marine Corsair squadrons assigned to support the invasion flew from escort carriers, providing combat air patrol over the landing beaches and striking Japanese positions with rockets and machine gun fire. The 8-square-mile island contained hundreds of fortified positions, pillboxes, and cave complexes that required repeated attacks to suppress or destroy. Corsair pilots attacking Iwo Jima's defenses expended enormous quantities of ammunition, often returning to their carriers with empty guns after single missions. The intensity of defensive fire from Japanese positions required that aircraft maintain their attacks, despite heavy anti-aircraft fire, making weapons reliability absolutely critical. Pilots who experienced weapon malfunctions during attack runs faced a grim choice: break off the attack and leave the target unsuppressed, or continue the run with reduced firepower and increased vulnerability. Corsair pilots rarely faced this dilemma because their weapons continued functioning through entire missions, regardless of how many rounds they fired or how violently they maneuvered. The Iwo Jima campaign lasted from February 19th through March 26, 1945, with Marine Corsairs flying continuous support missions throughout the battle. Armament crews aboard carriers reloaded thousands of ammunition belts, cycling through inventory at rates that strained the logistics system but never exhausted supplies. The industrial capacity that produced disintegrating link ammunition at Lake City and other facilities ensured that fresh supplies arrived regularly, maintaining the flow of reliable ammunition to forward units without interruption. This sustained logistical performance, matching the sustained mechanical performance of the weapons themselves, exemplified the systematic approach to military operations that characterized American capabilities. Japanese defenders on Iwo Jima observed American air attacks with a mixture of respect and despair. The consistent, overwhelming firepower that American aircraft delivered represented technological and industrial superiority that Japanese forces simply could not match with available resources. Japanese anti-aircraft gunners noted that American fighters would make repeated strafing runs without apparent weapon problems, firing continuously through multiple passes until their ammunition was exhausted. This sustained attack capability made defensive positions untenable once American aircraft located them, as the sheer volume of fire delivered would eventually penetrate fortifications or force defenders to abandon positions. The strategic bombing campaign against the Japanese home islands intensified during spring 1945, as B-29 Superfortress bombers flew missions from bases in the Marianas. Corsair squadrons from carriers provided fighter escort for some of these raids, flying long-range missions that tested both aircraft and pilot endurance. These escort missions required Corsairs to maintain formation positions for hours, while remaining alert for Japanese interceptors that might attempt to attack the bomber formations. When Japanese fighters did appear, Corsairs engaged them quickly and decisively, using their reliable weapons to destroy threats before they could reach the bombers. The reliability of American aircraft weapons during these extended missions provided crucial advantages that simpler metrics like rate of fire or projectile energy could not capture. A pilot flying a 3-hour escort mission needed absolute confidence that his weapons would function when combat began, regardless of how long they had been exposed to altitude cold, regardless of how many hours they had been subjected to vibration and thermal cycling. The Browning AN-M2 with disintegrating link feeds provided that confidence through proven performance across thousands of missions and millions of rounds fired. Japanese pilots attempting to intercept bomber formations knew from bitter experience that American escort fighters would have functioning weapons, a psychological burden that affected their willingness to press attacks against protected bomber streams. April 1945 brought Operation Iceberg, the invasion of Okinawa, the final major amphibious operation of the Pacific War. The campaign would witness the most intense kamikaze attacks Japan launched, with thousands of aircraft deliberately crashed into American ships in desperate attempts to halt the invasion. Marine and Navy Corsairs flew continuous combat air patrols over the invasion fleet, intercepting kamikaze attacks before they could reach their targets. The importance of weapons reliability reached its peak during these defensive missions, where every second of delay in destroying an incoming kamikaze increased the probability that it would successfully strike a ship. Corsair pilots intercepting kamikaze formations reported that their targets often disintegrated immediately when hit by .50 caliber fire, the combination of structural damage and incendiary effects causing catastrophic failures that destroyed aircraft within seconds. The reliable, sustained fire that disintegrating link systems enabled allowed pilots to be certain of killing their targets rather than merely damaging them and hoping the damaged aircraft would crash before reaching ships. This certainty was essential given the kamikaze threat profile, where even severely damaged aircraft could continue flying long enough to crash into targets. The cumulative statistics from the Okinawa campaign demonstrated American air defense effectiveness. Corsairs and other American fighters destroyed hundreds of Japanese aircraft during the 3-month battle, with Corsair squadrons achieving particularly high kill rates against kamikaze formations. While comprehensive statistics specifically attributing kills to weapons reliability versus other factors are not available in declassified records, operational reports consistently noted that weapons malfunctions were rarely cited as factors limiting combat effectiveness. American pilots could focus entirely on tactics and target prosecution, confident that their weapons would perform as designed when needed. Japanese aviation capabilities collapsed during the Okinawa campaign as pilot quality declined, fuel supplies dwindled, and industrial capacity finally proved inadequate to replace losses. The few experienced Japanese pilots still flying by May 1945 universally reported that American fighters were essentially invincible, not because Japanese pilots lacked courage or skill, but because American technological and industrial advantages had become so overwhelming that individual prowess no longer mattered. Among those advantages, weapons that worked reliably ranked prominently in Japanese assessments. American pilots could fire continuously through engagements, could trust their weapons to function regardless of conditions, and could focus purely on achieving firing solutions rather than managing mechanical reliability concerns. The atomic bombings of Hiroshima and Nagasaki in August 1945, followed by Soviet entry into the war and Japan's surrender on August 15, ended World War II before American forces invaded the Japanese home islands. Corsair squadrons preparing for Operation Downfall, the planned invasion of Japan, never flew those missions. The aircraft they would have flown, loaded with disintegrating link ammunition belts and armed with Browning AN-M2 machine guns proven through 3 years of combat, represented technological maturity that Japanese industry had never achieved and could not have countered even if the war had continued. The legacy of the disintegrating link ammunition system extended far beyond World War II. The system remained standard for American aircraft machine guns through the Korean War, Vietnam War, and into the jet age. Modern aircraft cannon and machine guns still use disintegrating link principles because the fundamental advantages that made the system successful in 1944 remain relevant in contemporary combat aviation. Reliable ammunition feed that works regardless of aircraft attitude, G-forces, or environmental conditions represents an enduring requirement that disintegrating links fulfill better than any alternative system developed since. The Browning A&M-2 itself remained in production through 1953, with over 85,000 aircraft guns manufactured during and after World War II. Many of these weapons served through the Korean War, where Corsairs flew close air support missions from carriers and land bases, their 50-caliber machine guns providing the same reliable firepower that had proven so effective in the Pacific. Some A&M-2 guns remained in service with reserve units into the 1960s, testament to the design's fundamental soundness and manufacturing quality that allowed decades of operational use. The industrial achievement represented by disintegrating link ammunition production deserves recognition alongside the weapon system it enabled. Lake City Army Ammunition Plant and other facilities produced billions of rounds of 50-caliber ammunition during World War II, each round precisely manufactured to specifications that ensured reliable feeding and consistent ballistic performance. The disintegrating links themselves, stamped by the hundreds of millions from spring steel, represented mass production excellence that Japanese industry never matched despite possessing theoretical knowledge of how such systems worked. American industry could manufacture precision components at scales that overwhelmed enemy production capacity while simultaneously maintaining quality standards that ensured every component functioned as designed. This industrial capability, more than any individual weapon system or tactical innovation, determined the Pacific War's outcome. Japan entered the war with experienced pilots, reasonable aircraft designs, and tactical doctrine based on years of combat experience in China. These advantages eroded steadily as American industrial production delivered weapons that worked reliably, in quantities that could not be matched, supported by logistics that maintained combat effectiveness despite operating across thousands of miles of ocean. The disintegrating link ammunition system exemplified this American approach. Identify a technical problem, develop a practical solution, manufacture it at scale, and sustain supply without interruption. Japanese industry could accomplish none of these steps consistently, and the cumulative effect of this industrial disparity proved decisive. The story of how linkless ammunition transformed Corsair combat effectiveness illustrates broader truths about technological warfare and industrial capacity. Individual weapons matter less than the systems that support them. Reliability under combat conditions matters more than theoretical performance under ideal conditions. Industrial capacity to manufacture and sustain advanced weapons matters more than scientific knowledge of how such weapons should work. These lessons, learned through the crucible of World War II, remain relevant in contemporary military operations, where sustained effectiveness depends on industrial depth and logistical capability as much as technological sophistication. For the Corsair pilots who flew combat missions from 1943 through 1945, the disintegrating link ammunition system was simply part of an aircraft system they trusted absolutely. They knew their guns would fire when triggers were pressed. They knew their ammunition would feed reliably regardless of how they maneuvered. They knew they could expend all 2,400 rounds without experiencing malfunctions that would leave them defenseless. This confidence, built through training and validated through combat experience, enabled the aggressive tactics that allowed Corsairs to dominate Japanese opposition throughout the final years of the Pacific War. The Japanese never expected American aircraft weapons to function with such absolute reliability because their own weapons could not match that standard. Japanese pilots planned tactics around anticipated malfunctions, conserved ammunition because they could not rely on sustained fire capability, and accepted that mechanical failures would often prevent them from effectively prosecuting attacks or defending themselves. This disparity in weapons reliability, subtle in peacetime but critical in combat, represented another dimension of American technological and industrial superiority that proved insurmountable for Japanese forces operating with degraded industrial capacity and disrupted logistics. The mathematical reality was straightforward and brutal in its implications. 6 Browning machine guns that fired reliably delivered more effective combat power than 8 guns that frequently jammed. A pilot who could fire 2,400 rounds without malfunction was more effective than a pilot who had to carefully manage 60 rounds of cannon ammunition prone to feed failures. An industrial system that produced billions of rounds of reliable ammunition overwhelmed enemy forces, armed with weapons that lacked such support, regardless of individual pilot skill or tactical innovation. The Corsairs' 2,400 rounds of 50 caliber ammunition fed through disintegrating links that separated cleanly and fell away without causing malfunctions, represented American military power in its most practical form. Not the most theoretically advanced technology, not the most sophisticated weapon system, but reliable capability manufactured at overwhelming scale and sustained through efficient logistics. This practical approach to military technology, perfected during World War II and exemplified by systems like the disintegrating link ammunition feed, defined American military effectiveness through the Cold War and beyond. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.